Hello, welcome to a drive-by code session. Welcome back. This is going to be number 4, I believe, in the series of making a programming language. If you have not seen the first ones, I recommend that you go and watch those in the series before coming back and continuing on this one in order to get caught up. So far, we have written a parser for a very basic, very limited programming language feature set. This is the grammar for it. We built the grammar using a tool called Nearly. And this is a file that parses some input supplied as a string, and it'll execute the parser on it, parse it, and then show you the result of the parse.js, and it says parse succeeded, and the result of the parse was a number. I'm also going to try out a different screen layout where the terminal goes on the right hand side and the code goes on the left hand side. Let's see how that goes. This time we're gonna add the ability to use some whitespace. So let's say, so currently the grammar allows a variable assignment like this, as you can see. However, the grammar does not allow whitespace like this. If the user of the programming language wants to be able to use some whitespace in between the assignment operator, he can, which is kind of a problem because without whitespace, your program can get difficult to read. So how can we fix this? Well, so we read this blog post called How to Grammar Good. If you're interested in learning how to build parsers, I recommend this. He recommended that whitespaces should be represented using, or this is one convention anyway. You can represent a optional whitespace as 1 underscore and mandatory whitespace as multiple underscores. And as you can see, this is a space character, and then the star means 0 or more occurrences of that thing. Well, my handwriting is super bad right now, but I'll let that go. Now that we have these guys defined, we can start injecting these symbols into our production rules in the places where we want to allow whitespace. So we're going to say here, for variable assignment between the identifier and the assignment operator, there can be optional whitespace, and then again after the operator there again can be optional whitespace. So now let's try that. We'll regenerate the parser, so that compiles it, and now we run the parser with the white space in between, and it accepts that. Okay, so that's white space. Well, next let's try to support the print statement. So in this programming language, we can write a print statement like something like this. You can say print and then a value here. Later on there will be expanded to allow arbitrary expressions as well. For now, let's just have a numeric value that you can print. So we'll define a print statement as the word print and then some mandatory whitespace and then a number. So given that, let's regenerate the parser. There we go. And then let's just print a number because that's what it supports right now. We can parse a print statement. Let's generate an AST for the print statement, which will say it's an object with a type of print statement. And its expression is the thing coming from this match over here. So you can think of this guy as an array containing the parts of the array are the symbols on the right hand side of this rule here. And so this guy here, that's data at 2. Is that at 2? That should be at 1 because I think this is 0, 1. Oh, no, this is at 2. Okay, so data at 2 is this number here. Rebuild the parser, and now we have this print statement represented as this object now. Let's allow the print statement to print arbitrarily complex expressions. Actually, at the moment we don't have arbitrarily complex expressions. In terms of expressions, we have numbers and identifiers. In any case, let's allow it to also print identifiers, which are like variable references. So we'll say an expression at the current moment can either be a number or an identifier. And everywhere we want to allow for an expression, we'll put expression there in place of number. And we'll use these ID functions to return the first thing in the match, because the right-hand side, there's only one symbol for these cases. So we say a print statement can now print an expression now, which can either be a number or identifier. Regenerate the parser, and we allow we allow the printing of an identifier now. Let's see if that works, and it does. Okay. So now, what else can we do? Let's have binary expression. What's a binary expression? Well, a binary expression looks like this. That's a binary expression. There's an operator here, and there's a number here, and there's a number here. There's two operands, thus binary. So let's make that work. So what does a binary expression look like? Actually, before that, Whitekit is going to distinguish between unary expressions and binary expressions. Unary expressions are not binary. It only has one thing in it. So an unary expression can either be a number or identifier. The definition of expression used to be like this, but we're going to extend that to say an expression can also be a binary expression, which is an unary expression, an operator with some assorted optional white space here and there, and then another unary operator. So unary operator, this could be a plus, and then another unary expression. So what's an operator? Well, this programming language can support add, subtract, multiply, and divide. So let's have those. And Whitekit wanted to be cute here and use the multiplication and division symbols here. I think my son would be very happy with that. Okay, because he's a math geek. Okay, so now we'll represent the binary expression as an AST object like this. The left-hand side comes from the 0th symbol from this match, and the operator comes from the 2nd symbol from the match, and the right-hand side comes from this, which is the 4th symbol in the match. The var assignment doesn't support expressions yet, so this is gonna fail. Yep, it fails. So he's gonna fix that by allowing var assignments to accept expressions as the right-hand side of the assignment. Regenerate, and now the var assignment can accept a binary expression, and you can see this binary expression is self-describing. It has a left-hand side of 1 and a right-hand side of 2 and an operator of a plus sign. And let's also, it works with multiplication too. So there's the multiplication. What about printing? That's the thing I wanted to see. It can also print a binary operation. See, so this is an object over here of type print statement. This object looks kind of squished here, but it's an object. I can assure you. So it's an object with a type of print statement, and an expression of the print is a binary expression whose left hand side is a, which is a identifier, and operator is the multiplication symbol, and right hand side is the number 2. Can it support more complex operations though. So can you do a times 2 and then divide by 5? Not currently. So how can we make that work? Well, this is where recursion comes in when it comes to grammar design. So we can actually say the right hand side, you could do it on the left hand side too, actually, with nearly. But in this case, we're going to do right hand side. We're going to say the right hand side of the operator is not an unary expression, but rather any expression, which could potentially be another binary expression. And just by doing that, we allowed the recursion to work, to allow these compound binary expressions that get chained one after another. So what would happen here is so this guy, given a times 2 divided by 5, this would basically say, first we have an unary expression, which is this guy, that guy, and then we have an operator, is that guy, and then the next thing is another expression, but this expression can be another binary expression. And then, so this guy, 2 is this unary operator again, and then this division symbol now is the operator, and then finally the 5 now is the expression. This time is an unary expression, and it happens to be a number. So we'll end up with a parse tree that looks like, that's what we're going to end up with. Let's see that guy in action now. Okay, so regenerate the parser, and there we go. We have this, the expression of the print is a binary expression that has another binary expression within it for its right hand side. So very cool. Whitekit decided to rewrite his parse script to generate AST files. So when you give it so you'll write your code in terms of files. So he uses a library called MZ, which is really handy for working with Node.js. It wraps all of the Node.js APIs using a promise-based way of calling the API. And we'll use async await to do this. If you're not familiar with async await, we have created a video series on that topic as well, so you can go check that out if you'd like. Okay, so now we're gonna read code from a file, which is going to end in .mypl as its extension, and then based on the base of the file name, we're gonna generate an output file that's gonna end in .ast. I'm gonna call into the parser, get the result, and then write it out to the .ast file. I'm actually gonna hand wave over most of this code. So basically, at this point, you can do this. Write a program in MyPL, in .mypl, like so. And call parse, passing in your program as the command line argument, and it writes out a new file called .ast file, but with the same base name of the file. So if you give it example1 MyPL, it outputs example1 AST. Let's see what that file looks like. So yeah, the output is the AST that represents this program here. This is a var assignment. We're gonna AST get that is a var assignment. Cool. All right, where are we now? So now let's allow multi-line programs. It's pretty messed up that this programming language can only give you single line programs, to support single line programs. So how can we support multi-line programs? So far we're saying the program can be one of two things. It can be a variable assignment, or a print statement. Well, no, a program needs to be able to support multiple lines. So we'll say this. This is merely a statement. What we called program before, that was merely a statement. And a program can either be a statement or a number of statements. Actually, we're going to define a thing called statements. And then we're going to say a program consists of a set of statements. How does this statements thing work, this rule? Well, we're using recursion again. We're saying statements can either be one statement, simply only one statement, or it could be a statement, a new line, and then some additional statements which calls back into itself. And simply by using this recursion scheme, you can have any number of statements now. We're going to do some AST stuff. Okay, so here at this point in time, we have a parser that can take any number of lines. This program just happens to have 2 lines and generate an AST that is represented as an array of statement objects. As you can see, this one has 2 variable assignments, and then you can see the second one happens to be a more complex one because the value of the assignment is a binary expression. So this is what we have now. I'm gonna try to note that parse. Now you have to supply the name of a program to parse. It's gonna generate an AST file for your program. Look at, and now we got 3 things in the AST now. Okay, so very good. Okay, let's parse while loops now. So what's a while loop? A while loop is gonna start with the word while, some mandatory white space. There's a binary expression that's gonna be the conditional, right? The conditional that goes. The while loop looks like while. We call this guy the body, or I should say this whole thing. This whole thing is the body, and the body is housed within these brackets. This guy, that's the conditional. So that's a while loop. So the binary expression is the condition. We'll have to extend it to work with comparison operators. And then those are the statement. The body consists of a set of statements, which is nice that we define a thing called statements. We can just reuse in here. And then we're gonna have some new lines, a statement, some optional white space here, and then the closing bracket here. This is the open bracket, this is the closing bracket. And we'll return the AST for the while loop as type while loop, and the conditional comes from the second match of these lists of matches. Again, think of these guys as an array of things, and the body is gonna come from the 7th. Let's count. So 7th, so you think of this guy as an array, right? So this is 0, 1, 2. Yeah, that's 2 goes here. This is 3, 4, 5, 6, 7. Yes, 7. That's the statements that goes into the body. So that's how we got the 7. But we don't care about those other symbols. We just care about this conditional and the statements. Okay. Now we need to expand the operator list to allow the comparison operators. And then now we should be able to regenerate the parser and be able to write a while loop. Where's my while loop? Oh, I think there's already a program that has a while loop in it. Or no, he's gonna write it now. Okay, so this is a while loop. This while loop's gonna loop 10 times by the looks of it. I'm gonna parse this program now. Something's not right. Let's figure out what it is. We forgot to include while loop as one of the possible statements. So add that in. to sort of turn on this rule. And now it's able to spit out an AST for while loops. This is really awesome. So let's do a side by side here. So first line is a variable assignment. That's that. And then the next statement is a while loop, which it starts from here and ends all the way there. There's a conditional, which is a binary expression. Left hand side is n, right hand side is 10, and the operator is less than. So you can see all of that here. And then the body of the while statement, there's two statements. First statement is this variable assignment there, and then the second statement is this print statement. So it all makes sense. All of this code is represented correctly by the looks of it, by this AST, and that's super cool. So that is the end of this episode. I hope you enjoyed it. In the next one, we're gonna finish off the building of MyPL by building a code generator that takes MyPL code, which looks like this, and generates JavaScript code. In other words, we're going to build a translator. It is commonly referred to as a transpiler. It's going to take the code in one programming language and translate it to JavaScript. I hope to see you soon.